Hi, my name is Jason, and along with my partner Sherjeel, for the past year, we've been working on the Part 4 project 113, Formant Analysis with Machine Learning. I'd like to give a special thanks to our supervisors Catherine and Dissen for being so helpful with this whole process. As an introduction to myself, my name is Jason, and I'm a fourth year computer systems engineering student currently doing my final year in my honors degree. So, as an introduction to the project, what is a formant? A formant is the resonant frequencies in the human vocal tract when a vowel is spoken. The vowel will create vowel vibrations within the vocal tract, and as you can see in the graph below, the peaks in the loudness shown on the x-axis are the formant frequencies, where one is at 700, one is at 1200, and the other is at 2500 Hz. This is created by the R sound in father. Going into project specifics, we want to analyze these formants using machine learning methods. There are two ways that we can analyze these formants. The first is through formant estimation. Formant estimation is the estimation of a formant frequency for a given, isolated segment of speech. This means that we only want to analyze this stationary segment without any regard to time. The second is through formant tracking. Normally, speech is a continuous signal with respect to time, and we often want to track the formant values as time progresses, whereas estimation needs the full speech segment when the speech is already uttered to estimate anything from. Hence, formant tracking is the estimation of a formant's frequencies tracks throughout an entire utterance, such as a sentence or a phrase. In this case, we will have a series of speech frames within a given time period that we want to analyze. The goal of this project is to compare machine learning methods of formant analysis to traditional formant analysis methods and find out whether machine learning is useful or even better for formant analysis in comparison to traditional formant analysis methods. The motivation for the study is that formants are important for applications such as speech recognition, but currently, traditional methods of formant analysis can be time consuming due to things such as manually looking at spectrograms to figure out what the formant is, or using a series of mathematical equations to deduce the vowel at specific frequency segments. Having a machine take the overhead for these calculations will significantly reduce the time taken to analyze the formants and hence allow for a broader application of formant analysis in speech recognition paradigms. To create the machine learning model, we have chosen to use Python as the main base of our algorithms. Python is extremely useful as there exist many different libraries for visualization and machine learning that could help us. The main machine learning library we will use is TensorFlow. TensorFlow was chosen as there is a plethora of documentation available online about it, and that it has a GPU accelerated version of itself, which means that we will be able to train on large data sets and allow the GPU to do calculations during the training and take the overhead that the CPU would normally take. The division of work is quite balanced in the fact that Sherjeel and I have done most of this project together, but the difference is in the formant estimation neural network creation. I did that, and Sherjeel had done the tracking neural network. Whereas with research, data aggregation, and visualization and conclusions, we did that together. For our research methodology, the data that we will be using for this project will be a set of data given to us by our supervisor, Catherine, and the data will have a fair selection of different speakers so that we can deduce how robust the machine learning model is. This data will originate from the New Zealand English database, and this research will focus on this database as the baseline for our conclusions that we'll draw. It is important to have our model work on different selections of speakers within this database, as it will show us that the machine learning model is not just able to predict one pattern of speech, but rather multiple patterns. To validate our research, we will be comparing hand-corrected formant frequencies for every vowel in the dataset to the predicted formant frequencies from our neural network. This hand-corrected frequency data will come from previously collected datasets where a person has manually labeled each vowel at each specific frequency, hence acting as the ground truth for our experiment. Since we will have a ground truth and a formant frequency prediction output from the neural network models, we will be able to check the accuracy through metrics such as mean absolute error over multiple iterations of our neural network. But how do we know if our results are a good fit? Essentially, we want to minimize this mean absolute error as much as possible, and then compare the mean absolute error for our model's prediction with traditional Formant analysis methods to see if our research has yielded any significant outcome, such that we'd be able to be confident in trusting the output from our neural network model over traditional Formant analysis. Now I'll hand it over to Sherjeel to discuss the second half of the seminar. Thanks for listening to me.
Thank you, Jason. Hi, everyone. My name's Sherjeel. I'm a PAT for Electrical and Electronics Engineering student, and I'll be presenting the rest of this project about Formant analysis using machine learning. Carrying on from what Jason has said, we use TensorFlow and Python to develop our models for performing Formant analysis. However, before we can make these models, we need to generate a set of input features that accurately represent our data. To do this, we use the frequency domain spectral envelope of the signal by using the linear predictive coefficients method, also known as the LPC method, along with a quasi-pitch synchronous spectrum to generate a set of complete input features. Doing this allows us to better capture the information that contains the Formant frequencies from the speech signals, and it puts us in a position for our model to make more accurate predictions without overloading it with too much unnecessary information. Once we've done this, we can carry on building our models. The first model we tested was the estimation model from Dissen and Keshet et al. 2016, which is a feed-forward neural network model. Now, the important thing to know about linear models like the feed-forward network is that the human vocal tract, which we are trying to model, likely exhibits nonlinear dynamics in Formant production because every person is likely to have slightly different vocal tract makeup, and to account for this, we need to use a nonlinear model. However, we do know from control systems engineering that linearity and thus linear models can work for such systems. We were aware of these limitations when we built our feed-forward model, but we realized quickly that we needed to introduce nonlinearities in the model to be able to achieve better performance and make better predictions. There's two main ways of introducing nonlinearity into models, and the first method we tested was using the concept of a recurrent neural network, which is a time-dependent network used to learn on sequences such as speech. To do this, we used a long short-term memory architecture, known as an LSTM, that is a very powerful sequence learner and can learn to predict long sequences of data, such as the Formant tracks that we want to predict. Doing this allows us to build a Formant tracking network instead of an estimation network, which can build on previous predictions carried out and thus allow us to generate predictions for entire utterances and speech signals instead of just training it on static segments of speech as in the estimation network prior. However, we ran into some issues that we will explain shortly with the recurrent architecture, and so we moved back to trying to improve the estimation architecture. Using work done by Dissen et al. In 2019, we decided to use another way of introducing nonlinearity into the model called a convolutional neural network. This is a network that uses the convolution operation to achieve nonlinearity, and we improved upon the architecture described by Dissen et al. By using a deeper architecture that allowed us to make better predictions. Here we're going to present some results from our study and explain the differences in the different architectures. Before I can move on to describing the performance of these networks, I'd like to explain the plots you see on the screen right here. The left side plots explain the neural network predictions and the right side plot explain the ground truth. These plots are the values of the first formant, F1, plotted against the second formant, F2, and each vowel will have a slightly different place in this plot according to how it sounds like. Up above, you can see the ellipses plotting the vowel space of the different vowels, and at the bottom you can see the individual vowels themselves being plotted so that we can track the actual shape of the vowel space and see how it changes between what our neural network can predict and what our ground truth can predict. Now, for the estimation network, we can see that the network does a pretty good job of preserving the details in the vowel space. However, we can see in some vowels, such as this bright yellow oo vowel sound, some of the detail in the vowel space is lost and the predictions are slightly shrunk. Moving on to the recurrent neural network model, we see some different results in a different direction. Because the recurrent neural network is a sequence learner, we learned that inaccuracies of any kind in the input data that is used to train it can confound the measurement and lead to values, frequency values of consonants and silent speech being learned as well, which allows it to better predict the performance of an entire track. But when measured using the performance in vowel formant frequency prediction specifically, we can see that the vowel space has shrunk significantly and finer details in the vowel space have been lost almost completely. Because of this, we decided to move on to the convolutional neural network and the estimation architecture as our most hoped for performance improvement. And we do see the largest performance improvement from this architecture. We can see that the vowel space is preserved almost completely in this architecture. It even predicts some outliers present in the data set that neither the recurrent neural network or the feed-forward neural network could achieve, and we can see that the vowel spaces, as described by these ellipsoids, are almost identical, which is another testament to the great performance of this deep convolutional neural network that we've built. Based on these results, we can easily say that our hypothesis of the nonlinearity in different humans, different vocal tracts is likely to be the cause of the inaccuracies in prediction, and deep convolutional neural networks are a very good way of modeling these nonlinearities so that we can arrive at a much closer representation of the different vocal tract systems that different speakers might have, so that we can predict our formant frequencies much more accurately and thus model the system much better. However, we are aware of the limitations of our data because we have trained on a New Zealand English data set that contains only speakers using New Zealand English, and thus we have no cross-accent data or speakers to verify our findings with. Future work would include training the neural network with such data and adding higher formant frequencies such as F3 and F4 to the mix as well, because these were also missing from our data set. Now, I'd like to move on to the demonstration of the project, for which Jason will take over. Thank you for listening.
Thanks, Sherjeel. I'll now be taking over for the demo for this project. In this demo, we will be showing you a run-through of how our system works, from training on the data to saving it and using the trained model to make a prediction about formant frequencies for our New Zealand English dataset. The first thing we do is create the machine learning model for the neural network via the TensorFlow API leveraged in this function, estimation model. Then we load data in from our file, which contains the extracted features from the speech signals. Taking this data, we then set it up so that it can be used as an input into our training network. We then clean up the data so that it can be used as input into our training network without issues. Then over here, we repeat the process for the second set of speakers we want to use for the training. Then the data is randomly shuffled here and divided into training and testing data sets so that we have training and validation data. Finally, we call the TensorFlow API and fit the model and train it, afterwards saving the trained model in a file for use in the next step. In the prediction step, most of the steps are the same. However, we load the saved model and use the parameters from the saved model to make a formant frequency prediction to test our training. As you can see here, we use the prediction model instead of a training model. Running the code now, shows that there will be a visual for our network prediction, F1, F2 frequencies, versus the ground truth running in real time that Sherjeel will have previously alluded to. Thank you very much for listening to us, and that was our demo. I'd like to thank everyone for being here and supporting this project.